Hello everyone, welcome to the next session on ANSYS Workbench tutorials. In this session, we are going to analyze a disc brake rotor for its thermal analysis. We are going to use the steady state thermal module of ANSYS Workbench. So we will start by double clicking on steady state thermal. Next I'll go to geometry and right click. Since I already have the geometry made with me, I will directly import the geometry here. Next, I'll go to model and double click on it. I'll first go to mesh and change the sizing to fine and update the mesh. Next, I'll go to steady state thermal and give the boundary conditions. So I'll right click and insert temperature. On this phase, I'm going to insert temperature of say 85 degrees Celsius. Next, on these three faces, I'm going to insert convection factor. Now I'm not giving a film coefficient here. I'll directly go to this option and click on import temperature dependent. Here you can see there are various options. I'm going to use the first one, that is stagnant air and horizontal cylinder for this case. I'll click on OK. So there are values of convection coefficient entered for various temperature profiles. You can see here, this is the temperature profile shown. Next, I'll go to solution and insert thermal temperature. I want to see the temperature change over the entire body. That is the heat distribution that is happening. Also, I will insert thermal temperature, and here I want to see the temperature of this particular surface. If you have gone through the video of static structural analysis of this disc brake rotor, you must have understood that this is the zone where all the values of stress, strain and factor of safety was less. So this was a critical area. So I want to see what is the temperature profile over that area as well. So I have chosen this temperature. Next, I will insert total heat flux, and I will also insert directional heat flux over this body. I want to see the heat flux along the x-axis. So I'll go to solution now and solve. We'll check the first result of temperature. You can see this is the temperature profile over the entire body. I'll click on max and min so I can know where the value is maximum and where it is minimum. As you can see here, maximum value as we have given here is 85 and the minimum temperature is 82.31. Next, I'll go to temperature 2 so that I can see the temperature profile over this area. Now, on the edge, you can see the temperature is 83.402. It is maximum because it is in contact with the outer surface. And here the temperature is minimum, that is 82.979 degrees Celsius. So you can see this temperature profile over only this section. And this is a critical section, so we are analyzing this separately. Next, I'll go to total heat flux. I can see the total heat flux over this body maximum is 0.005628 watt per mm square. The heat flux is approximately the same over the body. You can see here the maximum being 0.005 and the minimum is 3.36 into 10 raised to minus 6. So that's what you can see over this body. It is actually minimum in most of the places. Only in this critical zone, again, here you can see the value is maximum. So that's the heat flux over this body. And last we are going to see the directional heat flux. This is along the x-axis, so this is how I see the heat flux. If you want, you can also see the heat flux along the z-axis, which is also important, and along the y-axis too. So let's insert one more, that is along the y-axis, and we'll solve again. You can see this is the heat flux along the z-axis. The maximum value is still at the same position. The value of maximum heat flux is now 0.004222 watt per mm square, and the minimum value is minus 0.0011 watt per mm square. So that's the value now. And if I check the value along the y-axis, you can see again the critical zone is the place where you see your maximum heat flux. The value now is 0.003992 watt per mm square, and the minimum value is minus 0.00428 watt per mm square. So there is a variety of readings that you get along the x, y, and the z axis. But when you see the total heat flux here, this gives you an average value of the three directions. So that's generally considered, but if you are analyzing for a particular direction, then you can go separately for each of them so that you know as to what is the temperature in various places. Now, this analysis has been done by choosing the material for the disc brake as structural steel. If you want, you can change this material. So suppose if I change this material, generally in the automotive industries, grey cast iron or steel is the material used. So I will choose grey cast iron from here, and also I can choose stainless steel if required. We have already done the analysis by using structural steel. So let's choose these two materials, go back to project and update the project. Now I'll go back to my model, and here I want to change the material. So let's first analyze using grey cast iron. I'll go to solution and solve again. We go to temperature, highest is 85, and now the lowest value is 81.892 for this material. You can see here. Next we'll go to temperature 2 and check this critical zone. Here the highest value is 83.152 and the lowest value is 82.663. So that's the temperature profile over here. Total heat flux is 0.00558 maximum. The unit is watt per mm square, and the minimum is 3.339 raised to minus 6 watt per mm square for this body. Directional heat flux along x-axis gives these values. It is close to the value that I have obtained by using structural steel as a material, and this is what we obtained for the z direction, and this is the directional heat flux for the y-axis. Again, the values are close. If you want, you can check it for stainless steel as well by choosing the material, go to solution and solve again. So this is the temperature difference. Now by using stainless steel, you can see that the heat dissipated is little more. That is why the maximum temperature is 85 and the minimum is 75. Whereas in the previous two cases, it was around 80 to 83. Which means the heat lost is more over here. And temperature 2, that is over the critical zone, again you can see there is a difference. The highest temperature in the previous two cases was 80 to 83. Here the highest temperature is 79.2 degrees Celsius and minimum is 77.7, which means the difference is also there, quite good amount of difference, and you can see more heat is lost. Total heat flux you can see is 0.0049, which was 0.0055 in the previous cases. So here again it has lost more heat, you can say. Minimum is 2.94 into 10 raised to minus 6 watt per mm square. You can see the heat flux along the x-axis now. The position of maximum and minimum has not changed. It's just that the values have pretty much reduced, which means more heat is lost, which means the thermal conductivity of stainless steel is better as compared to grey cast iron and structural steel, and hence it is losing more heat, or rather I would say it's losing heat faster to the ambience. This is the directional heat flux for z-axis. Maximum value is 0.0037 watt per mm square, and the minimum value is minus 0.001. Let's check along this y-axis. Here the heat flux maximum is 0.0035 and the minimum value is minus 0.00379. So stainless steel could be a better material as compared to grey cast iron and structural steel. But again, it depends on the cost that is going to be incurred while making this kind of a disc brake rotor. So if the cost of stainless steel turns out to be more as compared to grey cast iron and structural steel, which it is, then in that case, going for stainless steel would be a matter of choice. If you are using thermal analysis and you want to lose more heat, then you can go for this material, or you can go for any other type of hardened steel which is good for this kind of an application based on how much heat it is losing. And which is the main criteria? Is strength the more criteria or heat transfer? So accordingly you can go for the material of this disc brake rotor. So with this I end the session. I hope you have understood how to analyze a disc brake rotor for its thermal analysis. If you have any doubts, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.